So here we have two materials, different density. We're trying to make them have the same mass. So you need to know that density equals mass divided by volume, which means mass equals density times volume if you rearrange that a little bit. So we want them to have the same mass. So that means we want gold on one side and lead on the other, and we want them to be equal. We want density times volume, density times volume, 587, to be equal to density times the volume, but that's what we're solving for. So we can call that x. So just a little bit of multiplying, 19.32 times 587. And then we're going to divide that by 11.34. You get x is 1,000.074. So that's pretty close to just 1,000 cubic centimeters. So here's another density question. What's the density of the concrete? Density equals mass over volume. So we know the mass, 339,292. We need to know the volume, so we're going to find the volume there. Pi r squared times h. Pi, diameter is 12, so the radius is 6, times the height is 20. If the volume is about 2260.8. The mass divided by volume. You get 150.076. This was pounds per cubic foot. So about 150 pounds per cubic foot. Here we have a pyramid with a pentagon base, a pentagonal pyramid, sliced horizontally so that the height is split into a 1:3 ratio. So that means whatever this height is, the height below is 3, which means the entire pyramid can split into 4 sections, 3 below and 1 above. So if we divide by 4, since it's split into 4 sections, we just need that upper part, which is 1 section of it. So divide by 4, the base is going to be 4 feet, because there's 4 total sections. And the base would still be a pentagon. You can see it cut right there, still a pentagon. With a 4-foot side. What 3-dimensional object or figure do you get when you rotate the following? So if you rotate a rectangle around the side right here, that's going to make a cylinder. If you rotate a right triangle around the leg, comes to a point right there. Wide base at the bottom, that's a cone. And if you take a semicircle and rotate it around the diameter right there, that will give you a sphere. The CDC conducted a germ study and found that student desks had about 13 million bacteria on them. Given that average school desk is 16 by 24, that would be the area. What is the bacterial density? So density for anything, whether it's population, in this case population of the bacteria, is the population divided by area. We know the population is 13 million divided by the area, 16 inches by 24 inches. It's 384 cubic inches. So 13 million divided by 384, you get 33,854.167, which we're going to go ahead and convert to scientific notation. That'll be about 3.4, maybe 3.39. Let's do 3.39. That's a little bit closer. 3.39 times 10 to the 1, 2, 3. Got to move it 4 spots. In 1991, the population of British Columbia was 3.3 times 10 to the 6. And there's land area. What's the population density? Population density is population divided by area. So 3.3 times 10 to the 6th divided by 9.3 times 10 to the 5th. You could just change that to be 3 with 5 zeros. Make sure you move it 6 places total. Over 9, 3 with 4 zeros. You got to move it 5 places total. So you get about 3.55 people per square kilometer. Here we have a knife, kind of looks like a sword, about to cut into this cube of cheese. So they're going diagonally. You can see it's a little bit diagonal right there. But it says that they're going to go straight down with the cheese. So that means the cross section would look something like that. Those sides are still right angles, even though it's a little bit strange looking, so that's a rectangle. It's not a square because the sides are squares, and that's a little bit longer than the side because they're going diagonally. And it doesn't look like a rhombus or a trapezoid, so. So if we stack congruent circles, think of like stacking up quarters. Put a quarter on top of another quarter on top of another quarter. That creates a cylinder. If the radii are diminishing, that means they're getting smaller. So if you put a quarter and then put on a nickel and then a penny and then a dime and then something even smaller and smaller and smaller, it's going to be coming to a point at the top. That would be a cone. If you take a circle, we'll pretend that that's a circle, and you translate it, just move it up, that would give you a whole bunch of circles, right? Stacked up, so that's also a cylinder. The M&M company, my favorite, is wanting to enlarge their holiday container by a factor of 1.5. The current container is cylindrical with a diameter of 3 inches and a height of 4 inches. It holds 480 M&Ms. Approximately how many M&Ms would fit into the new enlarged container? So even though the wording's a little bit off here, they want to enlarge all the dimensions, every dimension of their container by 1.5. So that means they're going to take the diameter. Instead of 3, it's going to be 1.5 times 3, which is 4.5. The height, instead of being 4, it's going to go 1.5 times 4. So it'd be 6. So you could figure out what the actual volume is, or you just take that scale factor which is 1.5. For volume, it would go to 1.5 cubed. If they do every dimension by 1.5, it's going to change the volume by a cubed factor. Which means by enlarging every dimension by 1.5, they're going to increase the volume by 3.375 times as much. So if it originally held 480, multiply that by 3.375, and it's now going to hold 1,620 M&Ms. So here's a case of balls being stacked into a box. So when you take a cross section, it just looks like the 4 circles in there. What would be a reasonable estimate for the area of one of the circles? So if it's 16 inches across, that means each ball is 8 inches across, which means a radius of one of them would be 4 inches. So area is pi r squared times 4 squared, so times 16. You get about 50.24 square inches. What is a reasonable estimate for the volume of a cylinder that fits into a box that's 5 by 5 by 10? So we've got this box. Something like that. 5 by 5 by 10. Which means that that cylinder that's in there it's going to fit across that 5 by 5 side. And it's going to have a height of 10. So that circle that fits in there, it's going to have a radius. Diameter is 5, so the radius is 2.5. So it's pi times the radius squared, 2.5 squared, and then 10 would be the height. So multiply all that out, and you get the volume is about 196.25 cubic inches. But here we've got a stack of pipes. We're supposed to hold 28 pipes altogether. This is only 9, so it needs a lot more pipes. So you can keep stacking them like this. So this would be 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Need some more. That'd be 19, 20, 21, 22. Finish this off. And one more row. Be about like that. That will be 28 pipes. So going down this side, it goes through the center of every circle. So you can count out how many diameters or radii fit all the way across that. If they tell us the diameter is 12, I would just go with diameter is 12. So that means this side here is 12 because that's a diameter, half of one circle, half the other. 12, 12, another 12, another 12, and another 12. So we end up getting a triangle. Looks a little bit like this. 1, 2, 3, 4, 5. 6 times 12 is 72. So this side's got a length of 72 inches. That's our hypotenuse there. We're trying to find the total height. The total height is going to go from the top of that circle all the way down to the bottom of this circle, which is not part of our triangle. So we're going to have to keep that in mind when we're done with this. Now, going this way, we can also count. There's a diameter and a diameter and another diameter. 1, 2, 3, 4 diameters, 4 12s. No, do that again. 1, 2, 3 diameters, 3 12s. So this is 36 inches. So you do Pythagorean theorem, 72 squared equals 36 squared plus x squared. And you end up getting that x is about 62.354. But that's not the total height. That just went from the middle of our top circle, the top pipe, to the middle of the bottom circle or bottom pipe. So we need to add on what's left over. There's 6 inches above the center and 6 inches below the center down there, because that's the radius. We need to add on the 6 and the 6. We're going to add 12 onto that to get a total of 74.354 inches. Find the total volume for the 2 congruent cones. So since they're congruent, we could just figure out the volume of one and then double it. Cone, so the volume is 1/3 pi r squared times height. Radius is 14. The height, the whole thing is 30. That means the height of one of them is just 15. So 14 squared times 15 times about 3.14 for pi, and divided by 3. The volume of one cone is 3077.2. So we multiply that by 2 to get 2 cones, which is 6,154.4 cubic feet. So here we've got a roll of wrapping paper. The diameter of the tube is about 2 inches. It's got a height of 36 inches. And the amount of paper wrapped around the roll is 1 inch thick. So it's 1 inch thick after the 2 inch diameter for that cardboard tube in the middle. What is the volume of just the paper on the roll? So that means you do the volume of the whole thing and then subtract the hollow center. So the whole thing has a radius, 1 inch of paper, and then the center has a 2 inch diameter, so 1 inch in the center. So the whole thing has a radius of 2. And the height is, what did it say, 36 inches? And then, because I think I'm funny, call it the hole in the hole. So the hole in the middle has a radius of 1. The height's still 36 inches, though. So we need volume. Pi r squared times h. Still pi r squared times h on this side too. So multiply that out, you get the volume is 452.16. And then $113.04. That's not a 4. That's a 4. So we subtract the hole with a W from the hole with an H. The whole volume minus the volume of the hole. And you're left with 339.12. That was all measured in inches cubed for the volume of just the paper. A circular island has a radius of 16 miles and a population of 34,000. Population divided by area gives you population density. So the population divided by the area. The radius is 16, so 16 squared times pi. So the area is 803.84. And then we do the population. Missed a zero there. 34,000 divided by 803.84. We get a population density of about 42.3 to the nearest whole number, so just 42 people per square mile. So here we're looking at the bottom of a jar. It's got a bunch of marbles in it. We're going to try to take the diameter, which we know is 6 inches across. But we want to know how many marbles fit across that, so we can figure out the diameter or the radius of a marble, approximately. So count out how many marbles. It's okay, we could be off by about a marble or so here. I would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, maybe 13 marbles. Going across 6 inches. If I counted again, I'd probably get 14 or 12, but 13 is a good enough guess. So that means that one marble is 6 divided by 13 inches. So the diameter of a marble about 0.46 inches, almost half an inch. So there's a couple ways you could go about this. You could figure out the volume of the entire cylinder, which will be pi r squared times h. So the radius is 3 times the height is 4. And you get that the jar has a total volume of 113.04 cubic inches. Then you can figure out if the diameter of a marble is 0.46, that means that the radius is 0.23. So the volume of a marble it's a sphere, so 4/3 pi r cubed. So you get that the volume is about 0.05 cubic inches. So you want to know how many marbles go into that jar? You divide 113 divided by 0.05. And you get that there's about 2,260 marbles in the jar. Another way you could have done it is just counted out how many marbles in the radius, which would probably be about 6.5 because we said 13 went all the way across. So I could say that it's 6, maybe 7 marbles is the radius. And then you'd have to figure out how many marbles would go across. So if the radius is 3 inches, it'd be a little bit more. Probably be about 8 marbles tall, which would be right because we said a marble is about 1/2 inch. So it'd be about 8 marbles tall for the height. And then you just find the volume in terms of marbles. So there's your radius, there's your height. And you do pi r squared times h. So pi times 6 squared times 8. Which only gives you about 904 marbles. But that's still a good guess because this first way of measuring it figures that all the marbles fit with no space in between, and we know that they don't fit that way. So I actually think 904 marbles is a better guess. Estimate, not a guess, estimate. Maybe 1,000 marbles if you want to round up. A right cone with a radius of 3 inches and a height of 7 inches. Describe the cross-section formed by a plane perpendicular to the base of the cone. So we've got the cone going this way. If we go perpendicular to the base, we're slicing it like that. And it contains the center. My cone is way off, but it's supposed to go through the center there. So when you slice a cone from the top straight down, you end up getting a triangle. In fact, you get an isosceles triangle because both sides of the cone are the same. The base of that triangle is the diameter. So if the radius is 3, that means 6 inches. And then the height of that triangle would be the height of the cone, which is 7 inches. Which means it looks like this. It's got a 6-inch base, and going down the middle, it's got a 7-inch height. And these two sides are the same. If you really wanted to, you could do Pythagorean theorem to figure out those two sides. We don't need to in this case, though. Find the volume of the square pyramid. It is a pyramid, so it's 1/3 the area of the base times the height. So since it's a square, this side's 30 and that side's 30, which means the area of that base is 30 times 30. And then here we're told the height is 8 inches. (2,400 cubic inches).